Welcome back, everyone, to the planetary science sample science seminar series. My name is Ian Malone. I am a graduate student here at UNM, and I'm excited to introduce today's host, today's talk, and today's speaker, Dr. Josh Wimpeny. He got his undergraduate degree in geology from the University of Liverpool in 2004. And then he went to study a PhD in isotope geochemistry at Open University, which he finished in 2009. Well, there he focused on understanding the behavior of the lithium and magnesium isotopes during the weathering process. Following his PhD, he spent 5 years as a postdoc at UC Davis working on a range of projects, including early solar system chronology using the aluminum magnesium system. Following his postdoc, Dr. Wimpeny joined Lawrence Livermore as a staff scientist in 2014. They started researching what we're going to be talking about today, understanding the behavior of moderately volatile elements, in particular zinc and gallium, and whether they provide evidence for volatile loss associated with a giant impact. Without further ado, Dr. Wimpeny.
Great. Thank you, Ian, for the introduction. And thank you, Chip, for the invitation to give a presentation today. Hopefully, you can all see the screen okay and can hear me. So I'll get started. So yeah, as Ian said, what I want to talk to you today about is some of the work we've been doing over the last, it's been a few years now, maybe 7 or 8 years, on moderately volatile elements, particularly zinc and gallium. And trying to, first of all, I guess constrain the isotopic compositions in lunar rocks and in the bulk silicate moon, and see whether that provides any evidence for loss of volatiles associated with the moon forming giant impact. Okay. All right, so we're going to start very simply with the fact that we know the moon is depleted in volatile elements compared to the Earth and chondritic meteorites. It's something we've known for a long time, and you can plot the bulk composition of the Earth, the bulk composition of the moon, or the bulk silicate Earth and silicate moon against chondritic meteorites, and you see a characteristic depletion trend in volatile elements. We're talking about elements with condensation temperatures of, say, around 1100 to 400 here degrees Kelvin, and you can see quite clearly that not only are both the Earth and the moon depleted in volatiles compared to chondrites, but that the moon is, for some elements, between 1 and 2 orders of magnitude more depleted in volatiles than the Earth. And so what I want to understand is when did this happen and how did it occur? So again, something that I think is pretty well known to everybody is that the leading hypothesis for how the moon formed is that a Mars-sized impactor called Theia hit the proto-Earth in what we call the giant impact. And this giant impact hypothesis has also been around for quite a long time. And it's kind of needs to account for a number of properties about the Earth-Moon system, including the angular momentum, but also the fact that the Earth and the Moon share similarities in their isotopic compositions, not just mass dependency, but also mass independent anomalies. And of course, it needs, well, I think we try to associate the volatile depletion with this giant impact event. Now, of course, it's possible, we don't know for sure that the volatile depletion was associated with the giant impact. In theory, the precursor materials, the building blocks of the Earth and the Moon could have been already depleted in volatiles prior to the impact event, or volatile loss could have happened afterwards, potentially. But I think most people would consider the giant impact as the leading way that we can account for volatile depletion. Okay, so within the kind of umbrella of the giant impact hypotheses, there are different models. Most people are probably familiar with the canonical model, where the impactor hits the proto-Earth. We form a ring of kind of a protolunar disk of liquid and vapor, and volatiles are lost from that disk, and then the Moon accretes from the volatile depleted remnants. And so, yeah, this is one way, and this way volatiles are lost from the moon or lost from the disk into vacuum. But there are some issues with this model in that it requires the majority of the moon to form from the impactor, and so there are question marks over whether you can get isotopic homogeneity between the Earth and the moon when you're getting the majority of material from one body. And then there are other models. I've put the synestia model here, but models where the Earth and the moon kind of equilibrated to some extent with each other. And in this case, we have different ways to kind of lose volatiles from the moon. So in the synestia model, we have this kind of structure with very high temperatures and pressures from which the moon condenses, and then volatile elements remain in the synestia and are accreted to what becomes the Earth. And there are other models, for example, Ni and Dauphin, and I'll show this later on in the 2019 study. They hypothesize that we get vapor drainage from the disk onto the Earth, and that happens at near to equilibrium conditions. And so there's different hypotheses about how we can actually lose volatiles from the moon associated with these giant impacts models. But the best evidence then that we have that volatiles were lost as a result of the giant impact comes from moderately volatile elements, so which is what we're talking about today. And so what exactly are they? So these are elements with 50% condensation temperatures, somewhere between 700 and 1100 Kelvin. Usually considered, for them to be useful for us, they need to have 2 or more stable isotopes. And elements such as zinc, potassium, gallium, copper, and rubidium. These are elements that we have actual data for from the moon. And like I said, I'll be talking mostly about zinc and gallium. And of these elements, I should point out, zinc is by far the most volatile. And in some studies, it would be kind of classed along with kind of chlorine and other elements that are considered more highly volatile. So it does behave a little bit different to the others. So why do we find these, why are these useful to us? I think there's 2 main reasons, two properties of the moderately volatile elements and their isotope systems. First of all, we know from looking at the Earth's mantle and also experimental studies here that their isotopics are relatively insensitive to igneous processing. So processes such as fractional crystallization, we don't see a lot of fractionation between minerals and melt, for example. So for zinc or gallium or something, maybe we're looking at sub 0.1 per mil differences between the isotopic composition of a crystallizing olivine and the melt phase. So this is really small. And what it means is that if we consider the evolution of the moon and the crystallization of lunar magma ocean, partial melting of Murray-Basalt source regions, these processes considered kind of relatively unimportant in terms of fractionating their isotopic compositions. And so we can basically kind of cut through that noise and in theory get back to a primitive isotopic composition of when the moon formed. And secondly, these isotope systems, because they're volatile, they can be fractionated by evaporative loss. And so what happens is that when these elements are vaporized, the light isotopes preferentially go into the vapor phase. And what that means is that the residue becomes increasingly isotopically heavy. Okay, so if we combine these 2 properties, it means that if volatiles were lost from the moon as a result of the giant impact, we can make some predictions about what we'll actually see. And so very simply, this is a kind of an oversimplification, but this is why these systems are quite powerful. If the moon lost volatiles as a result of the giant impact, we would predict that the moon should be isotopically heavier than the Earth, and that this should be a global signature. Because of course, in a magma ocean stage or due to heating during accretion, we would expect to homogenize any isotopic differences in the accreting materials. Okay, so we should see a global signature that's not really affected by magmatic processes. However, I say that But there is potential for these signatures to be overprinted by secondary processes, such as on the moon, redistribution of volatiles due to impacts or degassing. So it's not quite as simple as it seems. Now, there's been a lot of work done on this over the last 15 years or so, and some high-profile studies that have looked at the isotopic composition of moderately volatile elements, zinc, potassium, gallium, and seen isotopic differences between rocks from the moon and rocks from the Earth and chondritic meteorites. And so the first kind of high-profile study was back in 2012 by Paniello, and they showed that the zinc isotopic composition of the moon is, about 1 per mil, 1.4 per mil heavier than the compositions that we're seeing on the Earth. Although one thing you can note here is that there's quite a lot of heterogeneity in the isotopic compositions that they measured. So this would be consistent with loss of volatiles from the moon. We see then Wang and Jacobson 2016, a similar thing. For potassium isotopes, we see a distinct difference between the isotopic composition of the moon and the Earth. Again, the moon being isotopically heavier, which is consistent with loss of volatiles. Let me move on to other elements that are slightly less clear. So gallium, for example, that's what we'll be talking about to some extent today. And you see some variation in the isotopic compositions, but in general, again, it's leaning towards isotopically heavier on the moon than the bulk silicate Earth here in orange. And when I'm showing, when I'm showing this isotopic data, this is all in the standard kind of per mil notation. So this is the isotopic composition of a sample normalized to the isotopic composition of a standard in kind of parts per thousand, standard kind of way we do stable isotope variations. So we have plenty of data in the literature for moderately volatile elements. And what we see is if we actually plot the isotopic fractionation that we see in Murray basalts for different volatile elements as a function of their condensation temperatures, we see a rough kind of correlation that the more volatile elements, so here chlorine and zinc, we see more fractionation. And here we've got very refractory elements, we don't see any fractionation at all. So on the y-axis here, just to note, this is the isotopic difference between the moon and the Earth, but it is normalized to the mass difference. So these, you might, if you're familiar with any of this data, you might think, oh, this is not correct, but this is because it's been normalized for mass difference between the isotopes, because that's also a very important part of the extent of isotopic fractionation of stable isotope systems. Okay, so the red points here, or the pink points there, the compositions in Murray basalts, and then the average Murray basalt is in yellow. And the fact is that they're all isotopically heavier, or a lot of them isotopically heavier than the Earth. And if we kind of ignore chlorine for a second and kind of focus in on the elements from zinc upwards, what people have done is use the average isotopic composition of Murray basalts to estimate the composition of the bulk silicate moon. And based on these relationships, come up with kind of models for how volatile elements were lost. And so there are several different proposed fractionating processes. Of course, the initial study suggesting that loss of volatiles was associated with a giant impact. We have, as I kind of alluded to earlier, this model by Ni and Dauphin, suggesting that this is showing a vapor drainage from the moon to the Earth, or from the protolunar disk to the Earth. And then other models, there's been some discussion of whether we can get fractionation due to magma ocean degassing. And then recent work looking at whether this could be showing us fractionation associated with the Procellarum impactor. But in each case, the underlying assumption here is always that the average isotopic composition of the Murray basalts is representative of the bulk silicate moon. And yeah, I guess there's some potential problems with that. So first and foremost, something that we're going to investigate today is these isotopic heterogeneities that we see in the Murray basalt suite. So this is, again, literature data for zinc and gallium, and you can see the thing you kind of want to highlight here is that You can see the data for the bulk silicate earth in both cases by shown in the green band, and it's relatively homogeneous. But when we look at the isotopic composition of marine basalts, what we see is quite a wide range of compositions. And of course, as I said before, if this is a primary signal, we would expect to see isotopic homogeneity. Right, so any heterogeneity must be imparted by processes that are happening on the moon after it already formed. So based on that knowledge, it's probably not wise to just average the isotopic composition of these samples without understanding what's driving these isotopic differences. And in gallium, it's more extreme because the previous data was extremely, you can see there's a lot of variation. And on average, these compositions are not actually distinct from the bulk silicate earth. Okay, so that's how much heterogeneity we're actually measuring. So the other potential problem is that, earlier I said we're assuming that magmatic differentiation process is unimportant, but this is based on what we know of behavior in the Earth's mantle. And of course, the Earth's mantle undergoes convection, which the moon's does not. The other thing is that there's small isotopic fractionations. We know there are small isotopic fractionations between mineral and melt, and they're relatively unimportant on a kind of, when you're just looking at maybe a thin section scale or whatever. But if we're looking at the solidification of lunar magma ocean, and if we're getting constant kind of fractionation even to a small level, what happens by the time we get to 99.5% solidification by the formation of creep? Could that fractionation actually be significant, at least to generate an isotopically fractionated second reservoir? And then the other point to make is that we kind of like to group these elements together based on their volatility, but they have very different chemical behaviors. They partition into different minerals. They have different volatilities, of course. They can be fractionated by different processes. So it's not necessarily the case that understanding the behavior of one will help us understand the behavior of another. So what do we want to do today, or what do I want to talk to you about? Show you data for the isotopic composition of gallium and zinc in lunar rocks, the new data that we got from Lawrence Livermore National Lab. We want to say whether or not gallium and zinc compositions are isotopically heterogeneous as previously shown, and if they are, can we establish what the causes of these heterogeneities actually are, and produce new, more robust estimates for the bulk composition of the moon? And if we can do that, what then are the implications for the origin of the moon's volatile elements, and when maybe it lost volatiles? So this is kind of the sample list. It's a lot of samples that we've analysed for this project. So we've analysed mostly marine basalts. We also have some MG suite samples, and then 3 samples that we define as creep rich, and 8 fans that are interesting, but I'm not going to discuss here. So the creep rich samples end up being very important, and we define them based on their rare earth elements compositions. And so you can see here on this plot, chondrite normalized rare earth element abundances. So creep is usually defined by 15386, and it has a characteristic large europium anomaly and light rare earth element enrichment. And you can see that 3 of the samples that we analyzed, 14310, 72275, 14321, these are various breccias, basaltic clasts, impact melt, that show a similarity to 15386 that suggests they have a strong creep component in them. In contrast, we can see low titanium marrow basalt here, and green glass 15426, which we don't really see a lot of variation in their rare earth elements. It's worth noting also that the MG suite in red, so this is 76535, has a really pronounced light rare earth element enrichment, of course, because they contain plagioclase and they have a positive europium anomaly. So the europium anomaly is not necessarily a good one for tracing creep content. So in this study, we've used the lanthanum samarium ratio to kind of trace the enrichment in light rare earth elements as kind of a tracer for creep content. In terms of analyticals, I'm not going to go into this in really any detail. The samples, I would say that all the samples have both isotopic data and major and trace element data that we characterized here at Livermore. We didn't use the compendium data for trace elements. Zinc, we measured using a double spike to correct both the instrumental mass bias, but also correct for any kind of yield issues on the columns. And then we measured everything by multi-collector ICP-MS. And if anyone needs any more details on methods, I can definitely go into that, but I'm gonna leave it there. So I'm gonna talk just very briefly a little bit more about zinc and gallium, mostly because most people don't know much. They might know a little bit about zinc isotopes, but most people haven't done anything on gallium before. So they're actually relatively similar in mass, and they both have 2 or more isotopes, of course. Gallium is both siderophile, lithophile. It's much less volatile than zinc. Gallium tends to partition into, it behaves very similarly to aluminium, so they're both 3+, and it partitions into plagioclase. It's very incompatible in olivine. Zinc, on the other hand, is compatible in olivine, but does not partition much into plagioclase. So there are differences in volatility and chemical behavior. And on the bottom, I've plotted up kind of literature data for gallium on the left and zinc on the right in carbonaceous chondrites, non-carbonaceous chondrites, and rocks on the moon, just to show kind of the range of compositions that we see in solar system objects. And what you can see is that the range of compositions for gallium is relatively small. I mean, it's still much wider than the compositions we see in the bulk silicate Earth. So, primary igneous rocks from the Earth, but maybe a range of a couple of per mil. And contrast that with zinc, we can see just a huge range of isotopic compositions, but also elemental abundances as well. We're getting up to 400 ppm zinc, so a range of about 25 per mil. So that's a huge range of isotopic compositions. It's obvious that zinc fractionates to a much greater degree on the moon than for gallium, and that based on these enrichments, it's probably also more prone to being remobilized as well. So they are both classes moderately volatile elements. They do behave very differently. So let's move on to gallium isotopes. Okay, so quick recap. Why we care about gallium here? Well, the current understanding before we did this work was that the average isotopic composition of gallium based on Murray basalts, we can't resolve it from the Earth. So gallium really doesn't provide any evidence of volatile loss from the giant impact. We can't tell any difference between the moon and the Earth. And so what we wanted to do was confirm this isotopic heterogeneity and investigate whether we can actually calculate a better, a more reasonable delta 71 gallium value for the bulk silicate moon, or at least a better constrained value. So let's look at our data. So this is the data that we actually put this out a couple of years ago. And what you can see is that I'm going to use pretty much the same color schemes for all of these slides. So I've got terrestrial rocks in green, low titanium Murray basalts are in light gray, high titanium Murray basalts in dark gray, creep-rich rocks in yellow, and then Mg sweet and fans in red. With the gallium, this is the Caltech plot basically. So you've got gallium isotopes on the y-axis. And the thing to note here is that, first of all, our new data is better constrained than the previous data. And so we're actually, if we just average the isotopic composition of lunar basalts, we get a composition that is resolvable from the Earth. So this is consistent with loss of volatiles from the moon during the giant impact. But you do note that even with this better constrained data, it is more variable. Gallium isotopes are more variable on the moon than they are on the Earth. So the question is this value of 0.33 plus or minus 0.16, is that really a representative value of the bulk silicate moon? And so in order to kind of figure that out, we looked at some of the trace element systematics. So one thing we can look at is traces of lunar magma ocean crystallization. And so after plagioclase crystallization starts, we start getting a europium anomaly. So as that continues, as solidification continues, the europium anomaly will deepen, right? So that's one way to kind of trace crystallization within the lunar magma ocean. Also, compatible elements such as vanadium are increasingly removed. And so you can see in the bottom left a correlation between the europium anomaly, and in this case, we ratioed vanadium to manganese, going from low titanium marrow basalts up to creep-rich samples. What we can see is that the gallium isotopes loosely or broadly correlate with the europium anomaly in a kind of a similar way, in that the low titanium marrow basalts have the lowest delta 71 gallium value, whereas the creep-rich sample has the highest. And so, what is this telling us? Well, it could be telling us that gallium is being fractionated by progressive degassing of the lunar magma ocean. This would make sense because as plagioclase is being extracted, as the magma ocean is solidifying, if we're getting consistent degassing, then that would drive the lunar magma ocean to the residual melt to increasingly heavy values. However, there's a problem with this, and that is that really gallium is quite refractory, as it turns out. And so there have been experiments that have done that have shown just how refractory it is in silicate melts. But also recent modeling has estimated that you really get little to no loss of gallium by lunar magma ocean evaporation. So it doesn't seem to be able to explain this relationship. So instead, we should consider, how does gallium really behave in the mantle? Well, as I said before, it doesn't partition into olivine. So on the left-hand side, you can see kind of its behavior in partition coefficients in various mineral phases within the lunar magma ocean in the cumulate pile. So in olivine, really the D value is very low, so it doesn't partition. OPX is slightly higher, but it's still below 1. And then it's only really plagioclase in which gallium is compatible. So what this means is that actually, during most of the solidification of a lunar magma ocean, we're not getting a lot of gallium being taken out. It's only when plagioclase starts to crystallize. So the majority, plagioclase is really controlling gallium in the lunar magma ocean. So the majority of it's partitioning into these crustal cumulates. And so what we think is happening is that the gallium isotopes in marrow basalts are being fractionated or reflecting fractionation in the lunar magma ocean during extraction of plagioclase, or the extraction of gallium into plagioclase, I should say. And so if this happens with a preference for the isotopically light gallium, and we can see on the left-hand side kind of a Rayleigh fractionation curve. If we assume the isotopic difference between plagioclase and melt is about minus 0.3 per mil, then as we progressively solidify the lunar magma ocean, as more and more plagioclase is crystallizing, it takes out isotopically light gallium, and the residual magma becomes increasingly isotopically heavy, which is shown here. And this starting composition it's kind of irrelevant. What you can see is that we can generate fractionation on the order of 0.4, 0.5 per mil, which is about the range that we're seeing within our marrow basalts. And then we can regress the data that we have for gallium when it's plotted against the europium anomaly here. And if we regress it back to a europium anomaly of 1, we get a composition of about 0.1 plus or minus 0.1 per mil. So within uncertainty of the bulk silicate earth. And so what we think then is that the isotopic composition of gallium in the bulk silicate moon is much more similar to the composition of the bulk silicate earth than we would get from just analyzing the isotopic composition of marrow basalts. So this is based in first and foremost on the marrow basalt data. But is there evidence from fans to support this from anorthositic crustal rocks? And yes, there actually is. And so this is a really nice piece of work done by Jan Render, who was formerly a postdoc of mine and now a staff scientist here at Lawrence Livermore. And so what he did was analyze the isotopic composition of gallium in a number of different fans. And what we see is a correlation between the plagioclase anorthite numbers and the gallium isotopic composition. And so higher anorthite numbers, we're assuming crystallize first. And so what we see is that the plagioclase that's crystallized first, we have isotopically lighter compositions, and then the later formed plagioclase has isotopically heavier compositions. So this would be consistent with this model that we already have, where plagioclase is taking out isotopically light gallium. Okay, and so as it does that, the residual melt becomes increasingly heavy, and so later formed ferromanil orthosites have heavier isotopic compositions. And this is all consistent with, again, the bulk silicate moon, or the lunar magma ocean, starting with an isotopic composition of gallium that's basically the same as the composition in the Earth. Okay, so gallium isotopes, gallium is a moderately volatile element, but it does not trace volatility-driven processes on the moon. There's no evidence that gallium corresponds, for example, with zinc, and there's no evidence of gallium enrichments that we see for zinc, and it seems to be that gallium isotopes are controlled by magmatic differentiation. And so on the plot on the right-hand side, gallium isotopes don't provide any evidence to support this volatile loss associated with a giant impact, and rather than plot it, this average composition of the Mare basalts is not really very meaningful. In fact, the bulk silicate moon is probably here. Okay, so how about for zinc? So zinc's kind of a bigger fish in some ways, and that it's a higher profile system, and it's one that I think a lot of people know based on looking at people who do modeling and other things. And so so zinc is a very important system to understand. So let's recap again the current state of the game for zinc. Similar to gallium, actually. So the average composition of Mare basalts is fractionated from the Earth. And that's been used as evidence for volatile loss from a giant impact based on Paniello et al. In 2012, although I will say more recent studies have presented a more nuanced kind of version of that. I think better understanding that it's potential for some, do the Mare basalts really represent the bulk silicate moon or not? But the problem with the way things are right now is that there's significant isotopic heterogeneity within the Mare basalts. And so what we want to understand is whether the average composition really is representative of the bulk silicate moon. So this is our new data. So this is from a paper that's currently in review. And the blue line you can see here is the previous estimate for the isotopic composition of the bulk silicate moon. Okay, so plus 1.4 per mil. So we've got, like I said, the same color scheme here. We have the high titanium Mare basalts, low titanium Mare basalts, creep-rich samples in yellow, and then we have magnesium sweet samples in red. And note that there are some samples with isotopically light compositions that I've excluded from this plot. They're probably been affected by condensate addition, and because of that, they're not really useful for understanding the bulk composition of the moon. So if I average the Mare basalt data, I would get a composition of about 1.2 per mil, which is basically the same as previous studies. But with that, is that a reasonable thing to do? We've got a range of compositions from 0.5 to 4 per mil, whereas the bulk silicate Earth, based on, as I said, mantle-derived rocks on Earth, we're getting variations on the level of maybe 0.1 per mil. So what's driving all of this isotopic variation on the moon? Well, as it turns out here, what we see for zinc is a correlation between the zinc isotopic composition, again on the y-axis, versus indices for creep addition. And so on the left-hand side, we have the chondrite normalized. I missed off this chondrite normalized symbol, but yeah, it's the chondrite normalized lanthanum samarium ratio. And on the right-hand side, the zinc isotopes plotted versus chlorine isotopes in apatite. And in both cases, what you can see is a positive correlation between the zinc composition and these indices of creep addition. So, a creep would have a much higher would have a higher lanthanum samarium ratio, and is hypothesized to have a higher delta 37 chlorine composition. And so, based on this, then we would estimate that a creep has an isotopic composition of over the highest value here for the Mg suite, which is 3.8 per mil, so higher than 3.8 per mil. And so this would be this would be a highly fractionated N member on the moon. So this is not a great slide, but we can estimate the isotopic composition of zinc in creep based on the Mg suite. So if we consider that the parent magmas to the Mg suite are comprised of primitive mafic magmas, anorthosites, and a high amount of creep based on Steve Alardo's work in 2020, then we can kind of estimate the proportion of zinc in the Mg suite that must be derived from creep based on our own measurements, but also we've got estimated zinc concentrations in creep from Warren, and then kind of a range of isotopic compositions that we have considered for primitive mafic cumulates and for anorthosites. But as it turns out, it doesn't make, these N member compositions don't make a huge difference to this calculation. We know that the creep must have a composition above 3.8 per mil. And as it turns out, because creep has such a high, about 10 times higher zinc concentration, if we're putting 50% of it into the magnesium suite parent magmas, then the majority of zinc in the Mg suite comes from creep. And so we estimate that creep would have a delta 66 zinc value between 4.1 and 4.9 per mil, which is between 3 and 4 per mil higher than the values we're measuring in Murray basalts. So, okay, it's highly fractionated, but how did this happen? And there's kind of two main mechanisms. One of them is fractionation that accompanies the lunar magma ocean solidification. This can be done by magmatic differentiation, but our modeling suggests that this really can't drive more than 0.2, 0.3 per mil fractionation between mineral and melt. Fractionation by the time of creep formation. The other problem is that the high titanium Murray basalts, in this case, in any kind of progressive fractionation situation, we would expect the high titanium Murray basalts to have higher and more fractionated zinc isotope ratios than low titanium Murray basalts. When in fact, it's the other way around. So it doesn't really make any sense from a magmatic differentiation process from that standpoint for two main reasons. And the other way we could do it from a progressive fractionation scenario is through progressive degassing. It has the same issue though, in that the high titanium Murray basalts should have higher delta 66 zinc values than the low titanium Murray basalts. But the other problem is prior to crust formation, you need some way to separate the degassed material from the residual magma. And that, as it turns out, that's very difficult to do. It's very unlikely that we would get degassing into space, for example. And so the progressive degassing mechanism doesn't really work either. Now, I mean, degassing does seem to be the way that we get fractionation of creep. And so you can see on this plot, we've got the volatility of three elements, chlorine, zinc, and potassium, versus the isotopic compositions in creep and Murray basalts. And you can see that for these elements, there does seem to be a correlation both in the Murray basalt data, but also in the composition of creep. But this isn't a progressive mechanism. This is degassing of creep after it's already formed. Okay, so now we have evidence of complementary isotopically light zinc in the lunar crust, but we also have the fact that high titanium Murray basalts probably have a lower creep content, so the fact that they're less fractionated would kind of support some of this evidence. Okay, so then what caused degassing of creep? How did this happen? So some of this has been proposed previously by Jess Barnes, I think in 2016 maybe. So that would be the crust breaching impactor hypothesis. So there's two main ways. One is that we have passive degassing through the crust. So creep forms, sits at the base of the crust, and then degasses through cracks and fissures within the anorthositic crust. And this happens over a certain amount must happen over a certain amount of time in order to develop an isotopically heavy composition in Earth creep. And of course, we've got here degassing, but also condensation of that degassed material back onto the crust. The other way is as Jess Barnes had proposed, a crust breaching impactor. So an impactor basically cuts through the unorthocytic crust, exposes Earth creep to vacuum, and we get degassing this way. Now we prefer the passive, or what I call the passive model. So this keeps, there's two main reasons, or one main reason, that is that the most fractionated samples that we have is samples from the MG suite. And these, we know the parent magma is formed at the base of the crust. So it seems difficult to me, and maybe there's a way to do this, but to have a crust breaching impact to expose creep to the surface, degas it, and then bring it back to the base of the crust. To me, it seems more likely that Earth creep would just be in one place, and then it's free to interact with other melts, other magmas to form the parent magmas of the MG suite. And the other constraint then is that this degassing process has to have happened before the MG suite formed, and their ages are pretty well defined of 4.35 billion years ago. Okay, so what does this mean then? It means that the correlation between the zinc isotopes and the chondrite normalized lanthanum samarium ratio is caused by two-component mixing between primitive mafic magmas and Earth creep. Okay, and I've got that shown here on the left-hand side. And so in more detail, this is how it would work. We start with lunar magma ocean differentiation. And so the cumulate would develop a lower lanthanum samarium ratio. The residual magma has a higher lanthanum samarium ratio, but that differentiation doesn't affect the zinc isotopes. Once creep is formed, it undergoes the degassing process. And then we get mixing of reservoirs between the primitive compositions and creep. And then we have a sample array that kind of resembles what we actually have measured. Now, we wanted to estimate the isotopic composition of creep, and why is that important? Understanding the end member composition. Well, we know that creep is present in pretty much everything that was brought back from Apollo, and there's been studies to estimate how much creep is in, for example, the Murray basalt suite. And so studies by Snyder or by Lydia Hallis in 2014 have suggested that up to 2% creep-like material is in the Murray basalts. And so what happens then, we can play this game where we say, okay, let's take 2% creep out of kind of a primitive Murray basalt composition. So this is what we've tried to do here on the right-hand side. So using N-member compositions for creep for chlorine, zinc, and potassium, take away 2% creep from a kind of Murray basalt-like composition. And what happens when we do that is that we get these points for basically the composition of Murray basalt without any creep in it. And for chlorine, zinc, and potassium, and then you can see on the inset here, what happens is that we pretty much take away all the fractionation that we're seeing in these rocks. And so by just removing even a small amount of creep, we're having a huge effect on the isotopic composition of rocks of the Murray basalt suite. So you can, and you know, we're assuming N-member compositions. There's a lot of assumptions built into this type of calculation, but I think what it really highlights is that how important creep addition would be for the composition of moderately volatile elements, particularly chlorine and zinc in the Murray basalt suite. And so, yeah, creep-free Murray basalts, they have similar isotopic compositions to the bulk silicate earth and chondritic meteorites. We can kind of do this a second way, actually, and that's by regressing the zinc data when it's plotted against the chondrite normalized lanthanum samarium ratio. So if we regress it back to the lanthanum samarium ratio that's been estimated for a low titanium source without any creep, we get a isotopic composition of zinc that's, again, it's not very precise, of course, but we're within uncertainty of the bulk composition of the Earth and chondritic meteorites. Okay, so we've got two separate ways to kind of go back to basically a creep-free composition of the Moon, or of the Mara basalt source regions, and we get values that are, yeah, within uncertainty of the Earth. So one thing I guess I should say here is that, yes, we've got back to the composition of the Mara basalt suite, but is that then representative of the bulk composition of the Moon? And I think based on the previous slides that I showed, the only real ways that we can fractionate zinc would be through progressive fractionation due to differentiation, or through to progressive degassing. And I've already shown you that those processes are not very important. And so probably the composition that you see here is fairly representative of, if you believe me, is fairly representative of the bulk silicate Moon. Okay, so in contrast to gallium, zinc isotopes do trace volatility-driven processes on the Moon. However, the isotopic fractionation that we're seeing in many of these samples can be explained by variable creep addition. The zinc isotopic composition of Mara basalts is unlikely to be representative of the bulk silicate Moon. And in fact, this is what I think is actually happening, is that the bulk silicate Moon has very similar isotopic compositions of these of zinc, gallium, chlorine potentially, and elements like potassium. Of course, I haven't put uncertainties on this because the uncertainties are themselves quite uncertain. But from a kind of a first order kind of calculation, I think this seems to make some sense. Okay, so I note that I guess it's running out of time here, but implications of this work. So first and foremost, moderately volatile element isotopes on the Moon and the Earth. If you agree with me that they're the same, then it means they were not fractionated by the giant impact. Okay, so this means that their isotopic compositions must have been largely inherited from their precursors. Of course, you can also argue for some late accretion, which may have kind of muddied the waters a little, but in general, their isotopic compositions were inherited from their precursor bodies, from Theia and the proto-Earth. That doesn't mean that volatile loss did not accompany the giant impact. It means that their isotopic compositions were not fractionated, but it's still possible to lose volatiles without fractionating their isotopic compositions. This must have happened, if it did happen, under equilibrium conditions to prevent measurable moderately volatile element fractionation. And so one way that we can do this is going back to this vapor drainage model of Ni and Dauphin. So in their model, what they're assuming is that we have a protolunar disk consisting of a liquid magma layer, which is overlain by vapor. And then this vapor drains onto the Earth due to some kind of magneto-rotational instability, which I'm not sure I understand, but it drains onto the Earth. And that their model assumes evaporation happens into an undersaturated vapor medium. So they specifically did this to explain moderately volatile element isotopics. Okay, but we can remove that constraint, or I think we can. So the question would be, can we get a similar process happening at equilibrium without any fractionation of moderately volatiles? However, there is a kind of complication, and that complication is brought by rubidium strontium systematics. This is something that Lars Borg published back in 2022, and I think he's probably talked about this in this very seminar series. And so basically what he saw is that the initial strontium isotope ratios in boron and orthosites are very low 87, 86 values, which means the total permissible 87 ingrowth from the start of the solar system is also very small and requires that the Moon derives from material with a relatively low rubidium strontium ratio. And so it's not really possible, for example, for the precursors of the Earth and the Moon to had chondritic compositions, because the rubidium strontium ratio would have been so high that we should have ingrown much more 87 strontium. And what they also showed was, based on different mixing kind of models, that the moon was likely to be comprised of a significant proportion of Theia. So how do they get around the fact that we have similar isotopic compositions between the moon and the Earth? Well, they suggest that there are actually isotopic similarities in the inner solar system. So you could invoke that for both mass independency and also for mass dependent isotopes. So, for example, for the moderately volatile elements. And this has also been proposed previously by Nicholas Dauphin back in 2014. So I think of these two models, the moderately volatile elements, I mean, they can be consistent with either one. And whether or not you can kind of combine models somehow, I don't know. But yeah, I mean, yeah, I think what you can't have is a simple scenario where volatiles are degassing into a vacuum where you would expect isotopic fractionation to happen. It's just not. It's just there's no evidence for that. Okay, so I'm going to conclude there. So the moderately volatile elements, they're isotopic compositions in Murray basalts. They can be affected by post-accretion processing on the moon, such as magmatic differentiation for gallium and degassing of creep for zinc. This means that even though we have previously assumed that their isotopic compositions in Murray basalts are representative of the bulk silicate moon, that's actually unlikely to be the case. So their compositions, I think, are probably more similar to the bulk silicate Earth. This means that their isotopic ratios were not fractionated by the giant impact. If volatile loss did accompany the giant impact, we can't rule that out. It took place under equilibrium conditions. But an alternative scenario is that Theia was actually already volatile depleted prior to the impact event, and any isotopic similarity between the Earth and the Moon represents isotopic homogeneity within the inner disk. And with that, I'd like to acknowledge well, we have funding here from our LDRD program and also from NASA. I'd also like to acknowledge the support of the Survey agreement to Chip Shearer and the CASA Moon team, and to NASA CAPTEM and the curation staff for allocating the Apollo samples for us. And with that, I'm happy to take any questions.
Question for you in the chat. Let's see what we got. Looks like Tony's got a question about the creep mixing. The concept of creep mixing explains zinc isotope compositions. How do you reconcile the fact that zinc is largely compatible in olivine, such that concentrations of element in creep is much harder to reconcile relative to chlorine?
Sorry, I couldn't catch a lot of that. I think you said the concentrations in creep were high, or does he think they're too high, or I'm not entirely sure. I can't see the question.
Just say here.
Can I see the question?
Put it in the chat. I was going to put it in the chat.
Oh, hey. Hey, Tony.
Hey.
Sorry, I can't see the chat, so I couldn't really understand the question.
No worries. I'll say it again here. So
Yeah.
My question's about how do we reconcile the fact that zinc is not nearly as incompatible as other elements? So how are we concentrating it? How are we concentrating zinc and creep to make this work?
Right. Well, it is incompatible in plagioclase, so remember that. Yeah. I mean, I think. Well, first and foremost, it's been measured in 15386, so it is higher based on those measurements. I think you can. I've done some kind of modeling of based on various compatibilities of zinc in different minerals. It is compatible in olivine, but it is slightly incompatible in OPX, and it is it's not like massively incompatible. It's maybe 0.7 or something like that. But if you add all of that stuff up, by the end, you do get an enrichment in zinc in creep. It's not, as you say, it's not as enriched as chlorine, but you would get an enrichment, which is what is observed.
All right, thanks.
All right, and
read it out.
yeah, here we got one more question in the chat, and then Dr. Sharp has a question. So the question from Thomas talking about, let's see, could part of gallium isotope fractionation be related to possible gallium removal into lunar core?
So potentially, I don't know that we understand or know anything. Gallium, very few people have done much to kind of gallium isotope measurement. So I don't know what the partitioning is of gallium, or if there's any fractionation associated with partitioning into the kind of metal, basically. So it's possible that there is fractionation associated with the core, but it can't explain, to the best of my understanding, that wouldn't be able to explain isotopic fractionation that correlates with indices of lunar magma ocean evolution. At least I don't think it would.
All right, Steve, you had a question?
Yeah, I have a question. You compare chlorine isotopes to zinc and show the chlorine and the apatites being very high values. There's a paper by Tony Gargano and others that demonstrate that the apatite grades uniquely have the high chlorine isotope compositions, and that the bulk rocks are much more constant. And the interpretation is that the high values of the chlorine in the apatite is due to the fact that the apatites crystallize in its very, very last phase and are the product of an extremely degassed superficial magma, and nothing to do with the interaction with creep, because if you take the bulk compositions, they don't vary between phases. So on the one hand, I would think that making plots of the chlorine and apatite versus zinc is not correct, that you should use the bulk compositions, which he has in his paper. And well, that's the first question I have. And the second is just in terms of degassing creep when you have a thick crustal blanket on top of it. It just, we've considered this possibility as well. And it seems difficult to imagine how, are you doing it into a vacuum? Is the zinc that's volatilizing from the creep going into a vacuum, and then that vacuum reaches space through cracks in the solidified crust? And if it, I don't know how else you would do it, but I would also be hard pressed to see that the zinc would be able to escape very far at all without just reflating out with something. It's not a gas, so it's just difficult. I mean, it satisfies the geochemical constraints, but it seems to just fail on a fundamental thermodynamic basis in my mind.
Yeah, okay. So let me go back to I guess I'll go back to your first question. That was on, the difference between chlorine and apatites and then whole rock that Tony Gargano showed. And I mean, it's an interesting question, because no one understands this. Right? No one understands. As far as I've spoken to all the apatite people, and they don't understand this. They don't necessarily believe it either, I think. I understand what you're saying, but there's no easy explanation for it that I know of. I mean, I think, our bulk rock, I don't know how you then explain, the correlation between apatite and bulk rock systematics. That's challenging, the bulk rock kind of trace elements and isotopics. It's like I said, I've spoken to Jess Barnes and others about this, and I think they're left without any clear idea of how this works. And I'm not a chlorine expert, so I don't want to get into the disagreement. But I've read that paper. In fact, I took the data from Tony's paper and put it in this presentation. So I know the paper very well, and I've read it. I just there seems to be some disagreement there, and I don't know what the answer is. I think folks who focus on chlorine isotopes probably have some better ideas than I do. But when it comes down to it, bulk rock zinc correlates with chlorine and apatite. That's a fundamental observation. It also correlates with bulk rock lanthanum samarium ratios. Again, a fundamental observation.
Related to the same process. I know you know that. But
Well, maybe not. So the second, I'm going to go on to the second part while we have some time. So the second part was, what was the second part of your question? Sorry.
How you can have all these.
Oh, yeah, okay. So the degassing at depth. So I don't care. I don't really care how you degas creep. It doesn't bother. It doesn't bother me. To me, the most important part is that the most creep-rich rocks, or the rocks with the highest zinc composition, are the MG suite. So yeah, you can degas creep however you want. If you don't like the degas at depth, then sure, have a crust-breaching impact, or do whatever you want. But how then do you explain the fact that the MG suite, which formed at depth, then has this strong creep signature? We put forward the degassing at depth model hypothesis because it seems to make the most sense based on what we see in the MG suite. And because we don't know, sure, there's this big freaking crust or blanket. There's also, we don't know that for sure. We don't know what the permeability was of that, if there was any, exactly what the structure of that was at that time. And so, yeah, I can throw that out there. Why not? I think the clearest constraint is this from the MG suite. And so if you can degas creep at the surface and then get it back down at the base of the crust, then that's fine. That's fine by me.
All right, and then we have one more question in the chat from Ken Wang. He said, "Great talk, Josh," and he was wondering if the variation in zinc isotopes in the basalts is due to different proportion of incorporation of creep components, or is it due to a different process?
So there's a lot of variation within the basalts, and it doesn't follow the exact kind of trend that we see between the zinc isotope composition and lanthanum samarium, for example. So I think broadly, I think there's an argument to be made that if you just took the Murray basalts, but you could potentially see some indication that Apollo 15 low titanium Murray basalts show more creep in them, are slightly higher than some of the high titanium Murray basalts that are creep poor. But there are other processes that are probably contributing to some of the scatter in the plot. We know that we have samples that have, for example, condensate addition to them. 1017 is a clear example of that. And there are other samples that have been, they've been heated or brecciated, they've lost volatiles potentially. So there's various ways that we can get that kind of scatter in the plot. But I think the broad trend can be well defined by creep addition. Some of the other processes are probably needed to impart some of that scatter that we're seeing in the Murray basalts. And also, it's a tough measurement. So I think we've done a good job, but you can never rule anything else out. But yeah, I think, and of course, magmatic differentiation processes don't impart a huge fractionation, but small fractionations can occur.
All right.
Yeah, we ran out of time.
Yes. All right. Well, thank you for joining us today, everyone. Thank you. Special thanks, of course, to Dr. Wimpeny for doing a talk today.